I feel like you guys have been simplifying radicals in Algebra 1, in Geometry, and in Algebra 2, so hopefully this isn't going to be too crazy of a lesson, and hopefully the quiz won't be that crazy of a quiz. Alright, so we got a lot of quick, small examples to go through for this whole entire section, so just bear with it. It's going to seem like a lot, but they're pretty tiny. So, simplifying radical expressions. Are we ready? So, our first rule that we need to be aware of is the power rule for radicals. And the only time that the power rule can apply is when your index is the same for both radicals. If your indexes are not the same, then you cannot multiply them together. So if you have the nth root of A, and you're multiplying it by the nth root of B, then you can multiply the numbers underneath the radical, also known as the radicands, together, and make it become the nth root of whatever A times B is. Okay? And again, I can only iterate that. You can only use the product rule, thank you, when you are multiplying like indexes. So your index needs to be the same. Okay? All right, so for our first example, we're going to start out pretty simple. We've got the square root of 5 times the square root of 7. What would that get you? The square root of 35. Done and done. I'm just going to keep going on the same screen here instead of flashing back and forth. For part B, we've got the square root of 2 times the square root of 19. That would get me the square root of 19 times 2, which is 38. So far, so good. Part C. The square root of 11 times the square root of x. The square root of 11x. And for D, the square root of 7 times the square root of 11 x, y, z. Good. Square root of 77, x, y, z. All right.
Just a quick question.
Yeah.
If, say, that 77 was somehow had a square root, would we be, because it's being multiplied with the x, y, z, would we be able to simplify it or not?
Can you say that again?
If the 77 was, say, 64 or something that had
Yeah, then you could, right.
we could, even if
Yes.
it's being connected
Yep.
to the x, y, z?
Yep, and we'll get to those. Okay. All right, so now let's change it to something other than square roots. Let's do the cube root of 3 times the cube root of 12. I know this is C. Where did we leave off? This should actually be E, right? So this would end up getting us what? The cube root of 36. Is that a perfect cube? No. Because our perfect cubes are 2 to the third is 8, 3 to the third is 27, 4 to the third is 64. So no. All right. F is going to be the fourth root of 8y times the fourth root of 3r squared. Which would result in a fourth root of 8 times 3, which is 24. And then usually it's best practice to put your variables in alphabetical order, so I'm going to write my r squared first, and then my y. Okay, let's do an EFG. The sixth root of 10m to the fourth times the sixth root of 5m. That'll get us the sixth root of what? 50 m to the fifth. Okay? So we got our products down. Not too tricky. All right. So now the same thing can apply for quotient rule, which we've already kind of done. If you take the nth root of a quotient or a fraction, so the nth root of a all over b can be split up into two separate roots where you just take the nth root of whatever is in your numerator and the nth root of whatever is in your denominator. Okay, so if we do an easy one, the square root of 16 over 25 would be equal to the square root of 16 divided by the square root of 25, which is 4 over 5.
That's the previous slide.
Mm-hmm. Mm-hmm. Got it? No problem.
Oh, wait.
Go back.
Sorry. Yes, okay.
Okay. All right, so we have the square root of 16 25ths, which you would square root the numerator and the denominator separately, which gets you 4/5. For b, we have the square root of 7 36ths. So if we simplify that, the square root of 7 divided by the square root of 36. Can you simplify the square root of 7? Nope, so it's just going to stay the square root of 7, but the square root of 36 is a perfect square, which would be 6. For c, we had the cube root of negative 8 over 125. That would be the same as taking the cube root of negative 8 and dividing it by the cube root of 125. This cube root of negative 8. Negative 2. And then the cube root of 125 is 5, so negative 2/5. And I'm going to erase this top one up here. Let's throw in a d. So d will be the 5th root of x over 32. So what would be in my numerator? A 5th root of x all over, what's the 5th root of 32? 2, good. Okay, so power rule, quotient rule. Kyle, questions with that? Okay, so now we need to make sure we understand all the steps necessary for simplifying radicals. So this is where the harder stuff comes into play. So there's 4 steps that I want you to write down that we need to make sure is occurring when we say simplify a radical. So, condition number 1. So when you're asked to simplify a radical, you need to make sure all of these things are checked off. So conditions for a simplified radical. Number 1, the radicand, remember again, that's the number underneath the radical symbol. The radicand has no factor good one. Has no factor raised to a power greater than or equal to the index. Because if it is, then we can simplify it. Remember, we had problems already that was something like this. We had the 4th root of 6 to the 8th. Well, there my radicand has a factor that's raised to a power that is greater than the index, right? And what did we simplify this to? This ended up being 6 to what power? 6 squared, right? 4 divides into 8 2 times. Okay, so we got to make sure that my radicand does not have an exponent greater than or equal to the actual index. Second one, the radicand has no fractions. So if we have a fraction underneath our radical sign, we need to be able to separate it using our quotient rule and think about taking just the radical of the numerator and the radical of the denominator individually. So when we had the square root of 7 over 36, we get the square root of 7 over 6. So now my radicand up here is only a 7, so that's no longer a fraction anymore. And now I got rid of the radical completely in the denominator. So no fractions underneath your radical sign. And this is what we were talking about in section 8.2 where I said, oh, do we have to rationalize the denominators or not? And your book was not making you do it. But now we are eventually going to be getting there. We cannot have a denominator that contains a radical sign, which means you're going to have to end up rationalizing the denominator. And then the fourth one, exponents in the radicand and the index of the radical have no common factor except for the number 1. Now I'll explain more what that means when we get to a problem like that. Alright, so we're going to start off with simplifying radicals. And you've been simplifying square roots quite a bit. It's the simplifying of the cube roots and the 4th roots and the 5th roots that make it a little bit more complicated. So what I would like to do is quickly make a list of all of our perfect squares, perfect cubes, perfect fourths. So the list of perfect squares would be, what, 4, 9, 16, 25, 36, 49, 64, 81, 100. My perfect cubes. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. 6 to the third is 216. I'm not going to go any higher. And then our perfect fourths. 2 to the fourth would be 16. 3 to the fourth would be 81, right, because it would be 9 times 9. 4 to the fourth would end up being 16 times 16, so 256. I'm not going to go any higher than that. I don't know if we'll need fifths or not. Okay, so for our first example, simplifying the square root of 24. So when I teach this, maybe back in Algebra 1 as a freshman, you guys did factor trees all the way down to prime factorization. Me personally, I like to think about which perfect square divides into 24, which perfect square does divide into 24? 4 times 6. So isn't it true that the square root of 4 times the square root of 6 is the square root of 24? Yes. Simplify the square root of 4 to 2. Square root of 6 does not simplify. So that would be 2 square roots of 6.
Yes.
Yes, this should not be new stuff. The square root of 108. What perfect square divides into 108?
9 and 12.
9 times 12. That would work. It's not going to be our most simplified form, and that's okay. So the square root of 9 goes to 3, but now I'm left with a square root of 12. Can the square root of 12 simplify further?
Yeah.
Yes. What perfect square divides into 12? 4 and 3, so that would be 2 square roots of 3. Yeah, so then you would multiply that 3 and 2 together to get 6 square roots of 3, which probably means we could have done 36 times 3 to get to 108 right away. So 6 square roots of 3. How about the square root of 10? Let me simplify that. Is there any perfect square that divides into 10? Nope, so that's already simplified. So you can't simplify it any further. So you've been simplifying square roots for some time. Hopefully, this is not brand new information. If it is, just work through it. So now let's do perfect cubes and perfect fourths. Can I erase this?
Yes.
All right. Where is my first cube? There it is. The cube root of 16. So we're going to use the same philosophy. I want to figure out which perfect cube divides into 16. 8, right? So that would be 8 times 2. But now I'm going to do the cube root of 8 times the cube root of 2, which the cube root of 8 is 2, and now we're left with a cube root of 2. So it would be 2 cube roots of 2. What about, I'm going to add one on here, the cube root of 128. Which perfect cube goes into 128? 64 times 2, good. So putting cube roots over top of each of those factors results in what? Cube root of 64 is 4 cube roots of 2. What would change in my problem if I threw a negative underneath there with the 128? Where would you connect the negative to? Just put a negative in front of your 4, so it would be negative 4 cube root of 2. Because remember, you can have a negative cube root number. All right, how about a fourth root? Let's do the fourth root of 162. Which perfect fourth goes 81 times 2. So now I'm going to do the fourth root of 81 and a fourth root of 2. The fourth root of 81 is 2, and you're left with a fourth root of 2. If I put a negative underneath that, would you be able to do it? No. If I put a negative in front of it, would you be able to do it? Yes, and we'll just make it become a negative there. Okay? All right, so now let's throw some variables into the mix. Can I get rid of this? All right, so the square root of 16m to the third. So if you think about this in separate factors, I could just focus on the square root of my number separately, which would be the square root of 16, and then I can focus on the square root of m to the third separately. The square root of 16 is nice because that's a perfect square. That would just be what? 4. All right, so now we got to simplify m to the third. My index is 2. How many times does 2 go into 3? Once, right? So this is kind of the same as m squared times m, right? Because you add exponents. And if you take the square root of each of these, what would you be left with? Well, the square root of m squared is an m, and then I would be left with a square root of m. Now, me personally, I don't make these branches every time. I just know that if 2 goes into 3 once, I can pull out an m on the outside. What's left over, what's your remainder? 1m. So I would have an m on the outside, m on the inside. If this was the square root of 16m to the 5th, what would that look like? It would be 4. How many m's could you take out? 2. How many times does 2 go into 5? 2 with 1 remaining, right? If it was the square root of 16m to the 7th, it would be 4m to what power on the outside? 3 with 1 left over. So, whenever you have an odd exponent on any of your variables with a square root, you are always, always, always going to be left with one of your variables underneath the radical sign. If this would have been 16m to the 8th, then that would have just been 4m to the which power? How many times does 2 go into 8? 4, right? Okay. I know this is very dry, guys. Exponents are not my favorite thing in the world to go through.
Understandable.
Yeah. All right, so now let's go to a different power. Let's do a cube root. So the cube root of negative 8, x to the 4th, y to the 5th. Cube root of negative 8 is what? A negative 2. Good. How many times does 3 go into x to the 4th? Once. How many times does 3 go into y to the 5th? Once. So I'm going to have 1x and 1y left over. Now we got to figure out what is remaining underneath my cube root. So we said 3 went into 4 once. How many x's would remain if I took out 3 of them? 1. So I'm going to have 1x underneath. 3 goes into 5 one time, but if I took out 3, how many would I have left? 2. So I would have a y squared left over underneath. Okay, if you need to make the branches, this would be x to the 3rd times x. Cube rooting it gets you 1x cube root x. If you had y to the 5th, that would be y to the 3rd on a y squared, meaning that would go to your y. Cube root of y squared would stay y squared. Okay, all right, moving along. Let's do a 4th root. Let's do the negative 4th root of 32y to the 9th. We're almost there. The light at the end of the tunnel is very close. So we're going to have a negative in front. 4th root of 32. Not a perfect 4th. It's not on my list. So now I need to think which perfect 4th goes into 32. 16 times 2. So I have a 4th root of 16 and a 4th root of 2. So my 4th root of 16 is 2, and we're going to be left with a 4th root of 2 underneath my radical sign. So we're going to have a negative 2. I'm going to leave myself a blank and put my 4th root of 2 there. I left a blank because I think I can get a y out because my exponent is greater than my index. How many times does 4 go into 9? 2. So I'm going to have a y squared on the outside. If I took out 2 sets of 4, from the 9, which means 8, how many would be left over? Just 1, right? I've got 9 y's, and I took out 2 sets of 4, which is 8. 9 minus 8 leaves me with 1 y. So we got negative 2y squared, 4th root of 2y. Common mistake, some students will forget to carry that index over. Make sure you do that, because if you don't, then I'm assuming it's a square root. And again, we don't need to put absolute value signs, because our directions are telling us to assume that all variables represent positive real numbers. All right, so now we are going to connect what we just did last section with these types of problems. So we've got the 9th root of 5 to the 6th power. And we're asked to simplify it. Is my exponent in my radicand larger or equal to my radicand, or index? No, it's smaller, but I can still simplify this. Convert this into a fractional exponent. It would be 5 to what power? 6 over 9. And what does 6/9 reduce to? 2/3. Okay. So now what does that go back to as a radical? Cube root of 5 squared, which is the cube root of 25. So what about if we had the 4th root of p squared? And we're asked to simplify that. As a fraction, what would it be? P to the 2/4, which is 1/2. Convert it back. That would be what? Just the square root of p. Bless you. Last one. Here we go. NC. We've got the square root of 7 times the cube root of 2. What can we do there? Are they first the same indexes? No. So you would want to say, oh, I can't do it. Let's be done with it. But we can do something with it. Let's turn it into fractional exponents. So this becomes 7 to the 1/2. And we're going to multiply it by 2 to the what? 1/3. Yeah? Okay, so now let's think about this. Can I convert these fractions so that they have the same denominator? What would it be? It would be a 6th root, right? So this really is the same as 7 to the 3/6 times 2 to the 2/6. Why would I want to do that? Because now what will happen when I go back to my radicals? Won't they have the same index? So now this will become, am I getting too low for the back of the room there? I can move up here. So I've got 7 to the 3/6 times 2 to the 2/6. So now I end up with the 6th root of 7 squared times a 6th root of 2, hold on, that was not 7 to the 3rd, not squared. 2 is squared. So now can I multiply my numbers? Because now I have like indexes. Yes. So 7 to the 3rd, I don't know what that is. 7 to the 3rd is 343 times the 6th root of 4. So 343 times 4 is 1,372. So that goes to the 6th root of 1,372. Okay. That's probably going to be your most crazy problem for section 8.3. And that is it. Okay. All right, so you have the rest